Immiscible. What does that mean? I don't know that word. Not forming a homogeneous mixture. Got it. Today, I am going to tackle a P5JS simulation of the artistic process known as paper marbling. This is an ancient process. It involves water, taking ink or paint and floating it on top of the water, and then applying that to fabric, paper, ceramics, and all sorts of incredible and beautiful patterns emerge. The earliest accounts of marbling date back thousands of years to Japan, where the process was known as sumenagashi. A wonderful reference is the 19th century Japanese artist Tokutaru Yagi, who developed a method using a piece of bamboo to stir the colors. New marbling techniques were developed throughout the Middle East and Europe and continue to this day. I encountered the concept of marbling through the work of computational designer and artist Amanda Gasai, who collaborated with the studio Nervous System on a set of marbling infinity puzzles. Now, if we're talking about taking ink and swirling around in water, the first step might be to look at a fluid solver. And this is something I did in my coding challenge fluid simulation, and that was a bit of a mess, and it's incredibly computationally expensive. On Amanda Gasai's digital marbling post, she shows this wonderful WebGL fluid simulation demo that she built back in 2017. She goes on to reference this incredible paper by Aubrey Jaffer and co-authors called Mathematical Marbling, where Jaffer suggests that simple deformation formulas can produce a marbling effect without the need for such a computationally expensive full fluid solver. This method is also outlined on Jaffer's Mathematical Marbling website, and that's the primary resource that I'm going to use as I begin to write the code for this challenge. All right, so this is how I'm going to approach the problem. I'm going to consider my P5JS canvas as a tray of water. I then am going to drop a circular blob of ink into that water. And I want the ink to have two properties. The second property is a word I just learned, I don't know, a minute and a half ago, and I don't remember how to spell it. immiscible. This ink should be both incompressible, meaning its density never changes, and the same amount of volume of ink will stay within this canvas regardless of what happens, as well as immiscible, meaning if I were to pour another drop of ink over here, they aren't going to mix. Instead, one will push the other one out of the way. So my first step will be just to create an object that is that drop of ink itself. Let's create a file called ink.js for that class. And the drop of ink should be created at an XY position with a given radius. I'll write a function to draw it as a circle. And then I'll make an array where I can add drops of ink just by clicking the mouse. Okay, now I have a sketch with an array of drops. When I click the mouse, I add a new drop to that array, and then in draw, I show all of the drops. Whoops. Of course, I forgot to put ink.js in my HTML file. And I forgot that this dot's on. And there we go, drops of ink. So this is a nice start, but there's no actual marbling happening. I need that ink to be displaced when new ink arrives. In other words, imagine that I drop a blob of ink. We'll label that A. Then that second blob, B, is also dropped, overlapping part of it on top of A. Remember, the ink is incompressible, and the new ink is going to displace the old ink. Now, this isn't exactly right, but visually I'm going to get something like this. And this area should be exactly the same as the original area of the blob A. There are two approaches I could take here. One would be to actually look at all of the pixels inside of this circle and move each one individually to a new position, essentially creating this new shape. Instead, what I would like to do is consider this a closed shape and move all of the vertices of that enclosed shape according to the displacement from this new blob of ink. This is accomplished with Jaffer's formula. Given a point P, a vertex on that blob of ink, and a new blob of ink, a new paint drop of radius R centered at C, that point P has to move. So what direction should it move in? Well, it should move according to a vector that points from the new blob of ink to that point, P minus C. But how far should it move? Well, if that blob of ink is really big, it should move farther. That's accomplished by scaling the vector by r squared. But how far away is that point? If it was really, really far in the first place, maybe it shouldn't move very much. If it was close, maybe it moves a lot. This is accomplished by dividing r squared by the magnitude of that vector, p minus c. So hopefully that gives you a bit of intuition as to how this formula works. You can read the webpage and the paper for more details. Let's write that formula on the board. So P represents any pixel inside of A, but for our purposes, just the vertices around the perimeter of the circle. And C represents the center of the new drop of ink, and R represents the radius of that new drop of ink. Let's look at how I can apply this transformation formula in code. So first thing first, if I'm gonna deform that circle, I can't just use P5's circle function. Instead, I need to draw it myself, calculating all the points around the perimeter of the circle. So let's add a vertices array. And let's calculate all of the vertices using polar to Cartesian coordinate transformation. And let's start with just a small number of vertices, just 10. So if I'm counting from 0 to 10, I want those angles to go from 0 to 2 pi. So I'm iterating over the angles around the perimeter of the circle. I'm making a vector from the cosine and sine of that angle, scaling it by the radius, and putting it into the array. These points should also be offset by the original xy, the center of that circle. I might not actually need to save that center as separate x and y properties, but let's leave them that way for now. And then instead of using the circle function, I'll use begin shape, end shape, and iterate over all the vertices. This is the same, but you can see the circle looks more like a dodecahedron. Is that when you have 10? Because I'm only using 10 points. Let's make that a global constant. I'll call it like circle resolution. That is much too long of a name. Let's call it circle detail. And now let's up that to 100. And this looks much more like what we had before. Okay, adding the first drop of ink. There is currently one drop object in the array. Now, when I add the second one, I need to process all of the previous drops in the array before that second drop gets added to the array. That needs to happen right here. I'll call them other. So the idea is that I create a drop, then I marble all the other previous drops from that new drop and then put the new drop into the array. So all I need to do is write that marble function with that formula. So what is C? That is, a vector. You know what? Okay. Let's actually have the center be a property of the drop. I do need it after all, but let's have it also be a vector because that'll make the math stuff work better. As I embark on implementing the formula in the code, I will be making heavy use, just as I did with the center variable, of p5 vector. If the concept of vectors is unfamiliar to you, if you've never used create vector on the p5 vector functions, I would suggest taking a look at my Nature of Code chapter on vectors as well as the accompanying videos. But the quick version is a vector has an x and a y component. When I add two vectors together, I'm adding both the x's and the y's. Same with subtract. The magnitude is the length, and so on and so forth. And then here, I can just say add this dot center. Still working. Now I need to say take the center and add, oh, wait. Something is off here. I'm writing the code inside of the drop class, and I'm going to modify this object's vertices, which is not what I wrote here. Because what I wrote here is I said, hey, the drop is going to modify the vertices of the other. How to reconcile this? Who is marbling whom? I think it's fine. Other is going to get marbled from the drop. That's fine. It's fine. All the other drops get marbled from the new drop. And now I can iterate over my own vertices. And C is the other drop's center, and P is this drop's center. And what I'll do is I'll make a copy of it. This way I can say P sub C. And that now, P is now the vector P minus C, which is in both of these places. So I have C, I now have P minus C, and I have P minus C. I have R, which is, R is, other dot R, and square root I could do. So I have all the components of the formula now that I need. So P should be multiplied by, and let's call this root, is the square root of 1 plus R is other dot R. R times R is R squared, divided by P magnitude times, so let's put that in a variable called M. And in case you're wondering, that's what these absolute value symbols mean. That means the magnitude of the vector P minus C. The square root of 1 plus R squared divided by the magnitude of P minus C squared. Sorry to interrupt, there actually is a P5 vector function called mag squared, and that would be better to use here. So you use that, okay? All right, as you were. So P, which is actually P minus C, should get multiplied by the root, and then C should get added to it. And that is the new values of V. Let me try running this. Okay, so I've messed something up here. Okay, this is a major mistake that I made. What is P? Remember, P is the point that I'm trying to displace. It is all of the vertices around the perimeter of the circle. In my code, I just set P equal to this dot center, which is this point here. That's not what I want to do, although it shouldn't have totally disappeared. But anyway, let's fix that. It's a copy of the vertices. There we go. Whoa, marbling. Amazing. This is a little hard to see. Let's put some color in it, or at least grayscale. Let's say no stroke. And let's see what happens when, instead of clicking the mouse to add drops of paint, I do that automatically. And let's put this whole idea of what it means to add a new drop into a function. Whoa, that's a bit insane, but it is working. Let's make the canvas a little bit bigger. Maybe I don't want the drops to be able to be so big. Oh, I'm liking this better. See, it has that stone-like quality to it. This is a good start. I need to certainly think about where this is going. At some point, the deformations are going to become so skewed that the quality starts to suffer. The performance will eventually suffer because I'm never deleting any of them. But I think there's a lot that you could create from this alone. What if you add the drops of ink with some orderly geometric pattern? Or perhaps you think about other modes of interactivity. Maybe what if you were to drag the mouse around as you're adding ink? So coming back to my diagram, all that I've done so far is displace existing ink by dropping new blobs of ink into the canvas. But what if I were to take a comb over the canvas and wipe the ink? How could I get a displacement from doing that? And this is something that's referred to as a tine line. What would that math be? The formula for this is outlined here. The simplest place for us to start would be to just think about a single vertical line going down the middle. Imagine taking a toothpick and dragging it over the ink. Let's look at this formula. F of x of y equals, this is my new point. For every xy vertex in any drop of ink, I need to calculate a new xy. If the toothpick, the tine line, is perfectly vertical, there is no x displacement, only a y displacement. Only y gets a new value. Let's look at how I might do that. Now, in order to figure this out, let's not randomly add all of this ink anymore. Instead, in setup, let's start by adding just one single blob. And let me go back to a slightly smaller canvas. Great. Now I need a new function to add a tine line. And what do we need? We just need that x displacement, xl, if you will. So what does it mean to add a tine line at x equals 300? So we need a new function called tine inside of the drop class that just receives the x location of that line that's going to cause the displacement. And I'll just call it x here. Again, I need to go through all of the vertices. Each vertex is going to get a new value. v.x is just going to equal the original x. Then v.y is going to equal O. What's z? Well, z is a variable that I'm going to make up. Let's actually pass that in as an argument. And looking at the image here, there's actually two properties. There's z and c. These are controlling the displacement and the sharpness of the bend. So let's use those two variables. And let's try just with 20 and 1. Those are the first numbers from the image in the top left here. So I'm calling tine line with an x value of 300, a z of 20, a c of 1. Then that gets passed into every drop. And then we get those values here. But the formula has u in it. What is u? U is 1 divided by 2 to the power of 1 over c. Now that I have u, the new y equals the old y plus z times u to the power of the absolute value of x minus xl. Well, what is that? The absolute value of what is x? X is v dot x. And I don't actually need this because v dot x isn't changing, but it's nice to kind of have that in there just to remind ourselves. The absolute value of v dot x minus x. Okay, so this should be that formula for a vertical tine line. Let's see if it works. Yeah, look at that. No, it doesn't look like much yet, but let's add more drops. So let's put in a whole bunch of drops that will all displace each other in the center. So there's 10 of them. Now let's add that tine line. There we go. And let's play around with these values. Like give it a much higher C. Oh, look at that. We've made a lovely latte. I really need some coffee right now. This I think would be interesting to animate. So what if I actually took this tine line function and put it in draw? I'm just going to only do it if the mouse is pressed. Ooh, okay, that was way too much. So let's turn z all the way down to 1 because I want to apply the displacement over and over again. There we go. Now I should be able to also apply that wherever the mouse X is, right? So if I click the mouse here, yeah, look at that. Whoa. Let's add a lot more drops. That's too many. You can see how I can start to make all sorts of interesting marbling patterns. Now you might be noticing there's some harshness to the geometry on the outer edges, which is quite different in quality to the smoothness of the contours towards the center. That has to do with the amount of detail that I'm using to draw each particular shape. The larger ones now have fewer vertices. The vertices are spaced out. They all have the same number of vertices, but those vertices are spaced out more. I could certainly consider upping this circle detail, and we could see it's much more refined now. So it's going to be kind of a performance trade-off, but right now it's working fine even with a much higher circle detail. Already I'm really loving this pattern that I've got here. Just out of curiosity, let's try putting the blobs of ink in random spots rather than all in the center. Maybe I should speed up the marbling. Can make the Z value higher to do that, yeah. But I have only now allowed myself to apply those tine lines vertically. I could certainly do it horizontally. I'll leave this as an exercise to you, but horizontally would just be swapping the formulas here, essentially applying that same transformation to the X and no transformation to the Y. But what if I wanted to apply a tine line in any vector direction? Here is the answer under generalizations. This looks a little bit intimidating in terms of the new math that might be applied here, but I think we can handle it, especially if we lean on chapter 6 of the Nature of Code, where I look at a concept called scalar projection and the vector dot product. That's what's being referenced here on this page. Let's make our own version of the diagram. P represents any one of these vertex values on any of the blobs of ink. Then I have a vector, we'll call it M, which is emanating from a point called B. That is where the toothpick, if you will be dragged across the ink surface. You can actually, if we can get this to work, an exercise for you would be to think of it more as a comb, having multiple tine lines all at once, but let's not get ahead of ourselves here. So the formula is the new P needs to equal the old P plus Z times U to the D power times the vector M. So we have P, that's this point. We have M, that's the vector. The question is, what is D? Well, D is actually this distance. This is called the normal, a vector that's perpendicular to this line. And we can actually get that vector very easily by just rotating M by 90 degrees. And this is where scalar projection comes in. If we think of this vector, P minus B, we can actually compute D with the dot product. D is equal to the vector, this vector, which is P minus B, dot, this is different than multiply. It's a special vector operation known as the dot product, dot N, the normal. So this is the very first thing that we need to calculate. So I went through this whole effort of writing the tine line function, but ultimately I want to replace it with a tine line function that receives a vector instead of just a single X value. So let's take that out. And it should receive a vector as well as Z and C. But it needs more than just a vector, because this is the vector that I want to put in, but it also needs a position where that vector is originating, B. These are weird variable names. Maybe I need to rename them, but I need that vector, which is M. I'll call it V. Ugh. Let's call it V. And then I'm gonna use something called position, which could actually just be an X and a Y. Let's do that. And then Z and C. So ultimately, what I want to do is have a tine line. Let's just recreate the one that points down. Okay. So let's go back to what we had to see if we can recreate the latte effect. So I've got, and we don't need so many of them. We've got 20 blobs of ink. And I want to add a tine line that points down from the center. And then I need to give it a Z and a C. We'll just start with 20, 1. And this would be exactly the same. It's a little bit redundant what I'm doing here. We're just going to pass all these same variables into the function in the drop class. So now in the drop class, comment out this version of the function and add a new one with the new arguments. U is the same, 1 divided by 2 to the 1 over c's power. This is now going to be different. First, I need to calculate d. So what is p minus b? B is this xy position. And let's make a vector, I'll just call it pb for p minus b. And what do? I take this vertex minus b. So pb is now p minus b. And d equals the dot product of pb dot n. Oh, I need n. So what is n? Well, v is this vector m here. N is that vector rotated by 90 degrees. I'll make a copy of it. I don't know if I need to do that. And rotate it by half pi. So now I have d. D is the dot product of the normal and p minus b. V I need to displace. What do I need to displace it by? Oh, I've done something bad. I've got a real serious issue here. So I should call this m. Oh, I don't like that so much. But that's what it's called. I'm going to use the notation of the formulas, and then maybe I'll think about renaming the variables later. But I can't use v in two places. V is the variable that's the placeholder for every one of my vertices. M is the vector that is the direction of the tine line. I need to do this operation, z times u to the d power times m. So the first thing is I just need the magnitude of the vector, which is z times u to the d power. Okay, that's what the magnitude of the vector is going to be. And then I need to add to p a copy of m that is scaled by that magnitude. What's wrong here? Oh, dot subtract. I forgot the subtract. I said it, but I forgot it. And then I have another error here. P, oh, there's no p, it's v. Oh, look at that. I chopped it in half. Oh, d, oh, absolute value. Right. Because that dot product could be negative. So where did I get that wrong? This has to be the absolute value of this. Ah, look at that. Let's go back to like 16. Great. Now my timeline function, instead of being only vertical or only horizontal, can take any arbitrary vector as well as a position. Now, I did get that a little bit wrong, I think. I was talking about the position being exactly the point where the vector originates, but it really is just any point along the line. You can think of the timeline as an infinite line, and I just need to at least have one point along that line to know where it is. Not just the direction, but where it is relative to the blobs of ink. So, for example, if I were to change the direction to horizontal, I get that. Or even diagonal. It does need to be a unit vector. So if I'm hard coding in it, I mean, it worked anyway, but technically I've written it where it has to be of length 1. So I should say normalize. And now that looks a little bit more correct. Let's try the following. What if I were to drag the mouse to create a timeline? So I'm going to have a vector called start. And when I click the mouse, start is a vector at the mouse location. And then when I release the mouse, I'll finish the vector and apply the transformation. So I'll make a vector called end. Then I'll say end, subtract the start, end, normalize. And then I should be able to say tine line with that vector end at mouse x, mouse y with some z and c. So I'll just use the numbers I've been using, 80 and 16. All right, let's see if this works. Drag the mouse. Oop, what did I get wrong? Oh, I forgot that I had this in here still. That has to go away. That's no longer relevant. Okay. It's a little unfortunate that I don't see it while it's happening, but look at that. Now I can arbitrarily deform it. Okay, this challenge is done. I have developed the building blocks, a class for an initial drop of ink, the functionality for a new drop of ink to displace a previous drop, the math for a tine line to marble that ink along a vector path. And I think that's enough for this video. My challenge to you is, even with just these building blocks, how might you think about choosing a color palette for your drops of ink? How might you place the drops of ink in a regular or geometric pattern, as well as apply the tine lines in a particular pattern, like tines moving through a field of view in clockwise circular motions, or maybe arcs of increasing radius? There are also other kinds of displacement formulas that you could apply, like this vortex one. I think that I've given you the building blocks to go through and read further and apply some of these additional techniques. What about attempting this serpentine marbling like outlined here? You might also look at how Jaffer explains that paint drops can be raster rendered, meaning instead of displacing the individual vertices of a shape, what about iterating over all the pixels of a canvas and displacing those pixels based on an algorithm? You might even then move beyond abstract geometry and apply this technique to photographic images or real-time video. I think there's also lots of creative ways you could animate the ink being added to the canvas. Maybe it's not being added all at once, but slowly over time. How could you interact with the canvas beyond just the mouse through gesture or other means? Also, take a look at the link to the code that's in this video's description. I will go and revisit it, rename some of the variables, annotate and comment it to make it a little bit easier for you to follow and match it with the mathematical descriptions that are in the marbling paper. I say this all the time with the coding challenges that I'm curious to see what you make, but this one I actually I don't even know. I barely scratched the surface of this particular algorithm. So please, if you make something based on this mathematical marbling coding challenge, share it with me in the Passenger Showcase. Let me know your questions in the comments or things that I got wrong or missed. This is definitely one that I'm going to want to come back and revisit on a live stream and look at some of your creations and try to make more stuff myself. So have a great day. Thanks for watching this coding challenge, and see you next time on The Coding Train.